This lecture is on a special situation of refraction, and it's called total internal reflection and critical angle. Light will reflect inside a denser medium when it hits an angle greater than its critical angle. So I'm going to show you the situation for how that occurs. So you might remember from refraction, it goes from a low index of refraction to a higher index of refraction. And we have a ray of light, hits the surface of the water at an angle, and it refracts towards the normal. So the light ray bends. If you start out in the optically denser medium, in water in this case, the refracted ray will bend away from the normal, like in situation I. If you increase that angle of incidence, it bends a little bit more, and then it gets to an angle, which we call the critical angle, when the angle of refraction is 90 degrees. If the angle of incidence is beyond the critical angle, the light will totally internally reflect in the source medium. It has to be going from a higher to a lower index of refraction. So if you look at this turtle's reflection, we can see total internal reflection of the light there. Now, critical angle. It's the smallest angle of incidence for which light is totally reflected. So here's our critical angle measured from the normal. The light's coming from the optically denser medium, and it's bending away from the normal. The critical angle is when this angle of refraction is 90 degrees. So, what is the value of sine theta 2 when theta 2 is 90 degrees? So if you calculate sine of 90 degrees, it's 1. So if we go back to our Snell's law and we insert the refracted angle at the critical angle, we would have the index of refraction in the first substance times the sine of the critical angle equals the index of refraction of the substance the light's going into times sine 90 degrees, which is 1. So if our new equation is sine of the critical angle is equal to n2 over n1, where n2 is always less than n1. I'd like you to use n1 as the substance where the light ray starts, and it's a little easier to keep track of what's going on in your problem. So, just another way of looking at it. Here they have the sine of the critical angle is a ratio of your indices of refraction times the sine of 90 degrees, which they cancel to get n2 over n1. So total internal reflection can occur only when the light strikes boundary where the medium beyond has a lower index of refraction. Otherwise, your refracted ray will always be bending towards the normal, and you will never get a sine of 90 degrees. So here's our first example problem. It says, what is the critical angle for a ray of light traveling from a sapphire to ethyl alcohol? So if we look up the index of refraction for a sapphire, it's 1.77, and ethyl alcohol, or ethanol, is 1.36. The light has to start in the optically denser medium, so I have sapphire on the bottom and ethyl alcohol on top. So I start at my point. I want to find the critical angle. It's going to refract at 90 degrees in the ethyl alcohol when we're at the critical angle. My formula is sine of the critical angle is equal to n2, the substance of where the light is going, over n1, the substance where the light originates. When we solve for theta c, remember to take your inverse sine, and our value is 1.36 divided by 1.77, and our angle is 50.2 degrees. Any angle beyond 50.2 degrees will have a reflected ray. Where do we use this idea? Well, in fiber optics, which are just small strands of glass, Pulses of laser light go through, and it's totally internally reflected. Binoculars use total internal reflection. They produce the angle by cutting the glass prism, and let's go to the objective lens. The light comes in, look at the bottom of the screen, hits the first prism, flips your view, hits the second prism, flips it again, and then your eyepiece magnifies the image. So it's a two-lens system as well as total internal reflection. A bronchioscope also uses total internal reflection. Here's your original A, and it's projecting the A so the doctor can see it. Total internal reflection makes diamonds sparkle. So if you watch the red ray of light, hits the top surface of the diamond, totally internally reflects. That's what I describe as capturing the light for a while, and it makes the diamond sparkle. So here, the light's coming in. It's at a critical angle, so it totally internally reflects. Hits another side at a critical angle, so it totally internally reflects, and out it goes. So light gets captured in the diamond. If that angle is changed, so it's not as steep, the light still comes in, but we have refraction, and it's leaving here, so you don't get the brilliance. So near the bottom it says if the angle of incidence is smaller than the critical angle, then TIR, total internal reflection, occurs. Another, and this is a debatable one, but some people believe there's total internal reflection with polar bears, in that the light comes in and is totally internally reflected in their fur. I'm not sure what the verdict is, but heck, it's a cute polar bear. We should look at it. And the cutest, newest polar bear is in Denmark. Its name is Sikku, which means Arctic sea ice in Inuit. And his mother wasn't producing any milk. He was captured in the wild. So the scientists who found Sikku decided that it was better to take him back to the zoo and feed him and make him an ambassador for Arctic sea ice and to raise him. So anyway, a little bit on total internal reflection for you today.